So this is the video segment corresponding to section 1.3, in which I want to remind you how to do arithmetic modulo n, where n is some positive integer 2 or more, not necessarily prime. And then we'll finish by talking about Fermat's little theorem, which relates to the case in which n is prime. Now, if you've done the course Introduction to Number Theory, I'm sure you'll find all of this simple and easy, but I hope you'll manage in any case. So let me remind you that given any integer a, positive or negative, we can divide a by n, we've fixed n, and get a remainder r, which is unique if we suppose that r is at least 0 and no bigger than n minus 1. This is the so-called division algorithm, which I've mentioned at least twice. So the idea, of course, is very, very simple. We've fixed our integer n, we've taken all the multiples of n. Let's draw the multiples of n on the real axis. Let's suppose maybe n is 3 in this example, but I'll just say a. N, 2n, so I'm just putting points for the multiples of n, 3n minus n, and so on. As I say, let's pretend n is 3, so the only other integers that are missing are these ones here, I'm marking off. And having, let's emphasize the multiples of n, then of course an arbitrary integer is going to lie somewhere on this line. Let's suppose, for example, that a is here. And you see in this case, when we divide a by n, it goes twice, and the remainder is 2. I haven't drawn this to scale, but it doesn't matter. So the remainder here is this length here, which is meant to be 2. So that's the idea of the division algorithm. We're just comparing the integer a with the points which are the multiples of n. So that's our starting point. Now I want to remind you about the equivalence relation in which two integers have the same remainder modulo n. So that's going to be the definition of my relation. A1 is going to be said to be congruent to A2 modulo n if they have the same remainder, assumed to be in this set here, when we divide by n. And it's easy to see that statement is equivalent to saying that n divides the difference of these two integers. To see that one way, let's suppose we have a1, which is some quotient q1 n plus r, and then a2 is some other quotient, say q2 n plus, but it's the same remainder, so plus r again, r1 is equal to r2. Then if you just subtract those equations, you'll see that a1 minus a2 is a multiple of n, because the r's cancel out. So these statements are equivalent, and we can say this another way. It's easy to see this as an equivalence relation between two integers a1 and a2. That means that the equivalence classes will partition the integers into disjoint subsets. So what are the equivalence classes? They're given as follows. These are the equivalence classes. So if we're going to say that a1 is equivalent to a2, we're saying that these two equivalence classes are equal. These classes here, these infinite subsets are equal. So the first subset is just what you obtain by adding any multiple of n to a1. And you see what that set is, what they both are, will simply be the same thing you get by taking our fixed remainder r and adding any multiple of n to that fixed remainder. that's the same set. So those are the equivalence classes, and if they're equal, the two numbers are said to be congruent. Now, you see, I can also use this abbreviated notation. Instead of writing out this set here, which as I say Q is in Z, it's much easier just to write that set in this abbreviated notation, which simply means here we have an infinite set Z. So what this means is that we've just taken A1 plus any multiple of n. Okay, so this is just abbreviation for this infinite set. This equivalence class is actually a coset for the group with addition, for the subgroup corresponding to multiples of n. Here's the other equivalence class, which we're supposing is equal, and they're both equal, as I said before, though it's disappeared, just to taking the remainder plus all the multiples of n. And we can think, although these are infinite sets, we can think of them as entities in their own right, because they can be made into an arithmetical structure. So these equivalence classes, so this equivalence class, although it logically stands for an infinite set, you can think of it as just a single entity, and you often write it as R with a bar on top. So if these conditions are satisfied, they're all equivalent, we say that A1 is congruent to A2 modulo n. Okay, so I mean, let me just, I know this was elementary for many of you, but let me just draw you a picture again in the case in which n is 3 as an example. So when n is 3, we will have actually we'll have exactly 3 of these equivalence classes. We'll have all the multiples of 3, so let's suppose n is 3 as an example. Then we'll have all the multiples of 3, or if you like, that's the same thing as 0 plus nz, n here is 3. And I drew that subset before. It's just all the points on the number line which are multiples of 3. Suppose 0 is here. Then we could have 1 plus nz. Okay, so let's write that 1 plus nz. That's a difference equivalence relation in which the class, in which the remainders, when you divide by n, which is 3, are equal to 1. So these are these points here, in which the remainder is equal to 1. So all those blue points correspond to a single equivalence class, which you can also denote as 1 bar. This would be 0 bar. Should have done it in red. And then finally, we could have the equivalence class 2 bar, which is 2 plus n, in this case 3z. So here are the green points. So what we've done here is we've divided the integers up into 3 subsets, coloured red, blue and green, and these are the equivalence classes or residue classes corresponding to having the same remainder modulo 3. And then the point is, these 3 equivalence classes, we can think of them as entities in their own right, and we can do arithmetic to them that reflects the arithmetic from the integers. So to say that more formally, what we're saying is that we started with all the multiples of n, nz. That's an ideal in the ring of integers, and we can form the set of cosets, if you like, under addition, or these equivalence classes I described, and the set of those is the so-called quotient ring. And it's a ring because it has operations inherited from the integers. We can multiply elements of R and we can add them up. And a typical element of capital R, I denote little r with a bar on top. So, as I say, we can either use the notation of putting bars on top and just do arithmetic there, or we can use the equivalence relation notation. So, in any case, we can do arithmetic modulo n, however we write that out. So, for example, it's true that if a1 is equivalent to a2 mod n, then you can multiply both sides by any integer, and then AC is going to be equivalent to BC mod n. Okay, well, another way of saying that, of course, don't forget this is the same thing as saying that n divides a1 minus a2. So, I mean, it's obvious that implies that n divides a, so it's a1 and a2. Here it's a and b. I don't know, maybe this should be a and this should be b, sorry. So it's obvious that that divides AC minus BC is the same thing as A minus B times C. So it's obvious that this implies the left-hand side implies the right-hand side. Or if we want to use equivalence, if we want to use the notation of this quotient ring, we would say that A bar is equal to B bar implies that A bar times C bar is equal to B bar times C bar. Okay, moving on. Now I'm going to, should have had a pause here really, because I want to move on to the case in which n is a prime number. So things work better in this situation. I wasn't assuming that up to now. But if n is a prime number, then the key point is that the non-zero residue classes, so all I've done is I've removed 0 bar, they form a group under multiplication. Okay, R was a group under addition. In fact, under addition, we have the sort of clock face addition. If n is 3, we have sort of 3 points arranged around a clock face, and we can think of the elements of R 0 bar, 1 bar, 2 bar, and you add by just moving around the clock face. So 1 bar plus 2 bar is equal to 0 bar. But if we have a prime number, 3 included of course, we can also multiply the non-zero classes. So for example, 2 bar times, I use asterisk often for multiplication, 2 bar times 2 bar, that would be 4 bar, which is the same modulo 3 as 1. So 2 bar times 2 bar is equal to 1 bar. I must never get out of these 3 elements. 2 bar times 2 bar is 1 bar. Okay, incidentally, 2 bar plus 2 bar is also 1 bar in this case. So in particular, that means that 2 bar is the inverse of itself. And the key point is that these elements form a group. So another way of saying that, I've said consequently, but it's really the same thing as saying that if we have a non-zero element, x bar, then there's always an inverse. So there's always going to be a y bar for which x bar times y bar is equal to 1 bar. In other words, x times y has remained a 1 modulo n, which here is a prime number p. Okay, and the fact that you can find such a y bar, you need to use the greatest common divisor, property of the greatest common divisor we saw in the previous segment. I'll leave that as an exercise. It's easy to find that you can invert, you can find such an inverse provided we have a prime number. Okay, it wouldn't be true if n is not prime. For example, if n is 6, then 2 bar times 3 bar is 6 bar, which is 0 bar. So 2 bar could not be inverted in that case, nor 3 bar. So one other consequence of the fact that when n is a prime number is that if x bar squared is equal to 1, then it turns out that x bar is either 1 or minus 1, which is the same thing as p minus 1 modulo p. And the proof is straightforward, because if x bar squared is 1 bar, that's the same thing as saying that p divides x squared minus 1, or x minus 1 times x plus 1, and if p divides the product of two numbers, we know it divides one or the other. So that gives us this dichotomy, either x is 1 or minus 1 modulo p, and that's like it as in ordinary arithmetic. Okay, but that requires the fact that p be a prime number. Okay, so the last thing I want to talk about is Fermat's little theorem, and this is very easy to state. So we're still in the situation in which n is a prime number, and that means that the non-zero residue classes form a group. That group will have order p minus 1, because we've removed 0. And if you have a group of a given order, any element to the power of that order, if you multiply any element by itself that number of times, you're going to get the identity. So if we take an element of the group, that means, for example, we can take a, where a is between 0 and p, then what we're saying is that a bar, if you like, to the power p minus 1, that means multiplied by itself, so we have a total of p minus 1 factors. This is equal to the identity in the group, which is 1 bar. Or another way of saying that is that a to the p minus 1 is congruent to 1 modulo p. So I was trying to show you what was missing there. A bar to the power p minus 1 is 1 bar. That's the same thing as this statement here. Now, we can make this statement a bit more general by multiplying both sides by a. So if we multiply both sides by a, if this is true, then from what I said before, this is certainly true. The statement is certainly true. This certainly implies that. But the point is, we can now remove the restriction that a is essentially what I was saying here is that a is not divisible by p. A is non-zero as a class. And we can remove that restriction now, because this formula will also be true if a is divisible by p, or if a bar is 0. It's obviously true if a bar is equal to 0 bar, because both sides will be 0 bar. So, if you like, we can rewrite that as a bar to the p is equal to a bar. So if a bar is 0, obviously that's true. So this is more universally true. This statement here is more universally true. It's true for any integer a. So that's a consequence of the group property. So it's an easy fact, but it's known as Fermat's little theorem. I want to finish with an example. So the example consists of the following. So this time, rather than fixing n, I'm going to fix the integer a. So I'm going to take a to equal 2. I'm going to fix a to equal 2. I'm going to allow the exponent in this theorem to vary. In fact, I'm even going to allow non-prime numbers. So I'm going to study 2 to the power n minus 1 for any integer n. And I'm going to ask, if n is a prime number, we know that 2 to the p minus 1, 2 to the n minus 1, has to be congruent to 1 mod n, mod p. So I'm going to ask, when is this true? When is 2 to the n minus 1 congruent to 1 mod n, without necessarily assuming that n is a prime number? And so I can just test this. In fact, I just did this on the computer. But what I get is these numbers here, and virtually all of them are prime. So actually, although, I mean, the theorem doesn't tell, the theorem tells us if n is prime, then this has to be true. So we know that this list has to contain, the list of numbers where this is true, has to contain all the prime numbers. But it could contain others. Fermat's little theorem doesn't tell us that this only works for prime numbers. But as you see, it only contains 2 others, because in manufacturing this list, I also factorise the numbers. So there are only 2 numbers in this list. That's up to 599. There would be further numbers if I went on. But up to 600, there are only 2 of these numbers for which this relation, Fermat's little theorem relation, holds. But n is not prime. The 2 numbers are 341, that's that one, and the bigger number is 561. They're both divisible by 11. I factorised them there. So what we're doing here is we're actually using Fermat's little theorem to detect prime numbers. It's a very powerful method, actually. Even by just fixing a to be 2, we've got almost exactly the list of prime numbers from 1 to 599. We've just got 2 sort of erroneous entries in the list, 2 fake prime numbers, or they're sometimes called pseudo-primes, corresponding to a is equal to 2, because they pass Fermat's little theorem test, but they're not actually prime numbers. Okay, of these 2, the second one is particularly important. It's an example of something called a Carmichael number. But I'll stop there.